Hi everyone, and welcome to another QtDay talk. We're just about to watch the recorded video called What's New in 3D for Qt 5.14, 5.15, and beyond with Mike Krus. So let's bring him on so everyone can see him, and I'll present him to you all. So hi there, Mike. Good to have you here. Welcome.
Hi, good afternoon, everyone.
Good afternoon. So let me tell you all about Mike here. He is a senior software engineer at KDAB and has been developing with C++ since 1996 and with Qt since 2004. He has a broad range of experience in scientific applications, mainly in civil engineering and oil and gas industries. And his range of expertise includes C++, QML, and interactive 3D visualization software design on desktop and mobile, as well as macOS development. Mike is the Qt maintainer for the tvOS platform, one of the core contributors to Qt 3D, and is very interested in building mobile applications with Qt, mainly on iOS. And he has a PhD in computer science. So in this session, we'll review the changes in Qt 3D in recent and upcoming releases of Qt, mainly in 5.14 and 5.15, along with plans for the Qt 6 timeline. We'll look at how Qt 3D compares with the upcoming QtQuick 3D. And finally, we'll look at upcoming changes in Kuesa, an extension to Qt 3D to integrate with authoring tools. And the use of 3D-related technologies continues to grow year after year. So I hope you all enjoy this talk. Do you have anything to add before we go through the video?
No, that was written back in April when the original conference. So there's actually lots of new stuff about the things that actually is going to ship in Qt 6, so rather than timeline information. So there is lots of new stuff.
Okay. We might have time to talk about it a little bit. We'll see. All right, so everyone, if you have questions to ask him during the video, please direct them to the Q&A chat. That's the one next to the room chat with the question mark icon. It's not the help button. So please ask your questions there just to keep things organized. All right, so sit back and enjoy, and we'll see you after the video. Thanks.
Right. Hello, everyone. Welcome to this talk. My name is Mike Krus. I work for KDAB. KDAB is a provider of services and training around Qt technologies. And one of the things we do is invest quite a lot of time in R&D, in actually writing Qt features. KDAB is the main contributor to Qt source code outside the Qt company, and one of the things that I do with some of my colleagues is work on Qt 3D. So what I'm going to talk about in this talk is some of the things we'll be doing for Qt 3D, Qt 14, 5.14, 5.15, and the upcoming Qt 6 talk. So some of the things I'm going to talk about are actually about a year old, but because this talk was delayed, then I'm just coming back through them here because stuff that might not have been published on our blog, but hopefully it'll still useful information here. And then I'll talk about some of the new stuff that we are releasing for the Qt 6 release in the next coming weeks. So briefly, before I go into details, what is Qt 3D? So it's a library, general purpose 2D and 3D rendering library that ships with Qt. It's been available since 5.9, I believe, as an official module. And architecture-wise, it's based on an entity component system. So you build a tree of entities and give components to them, and you have several systems which basically take the data that comes from the entity and apply some simulations if you want. So one of those, of course, is rendering, but you have other what we call aspects to do input handling, animations, that kind of thing. It has it's all written in C++, of course. It has a C++ API, but it also has a QML API, which is almost identical to the C++ API. It comes with a very versatile renderer, which can do lots of things, from simple forward rendering to more complex multi-pass rendering, with lots of effects that you can write. And it scales from low-end embedded hardware all the way to desktop class systems and more advanced rendering. So new things that we did in 5.15, 14 and 15 mostly are related to performance updates. So Qt3D has, as I mentioned just previously, has front-end and back-end. So you have your front-end with all the API nodes that you use. And these are just data, so they're classes that derive from QObject and have properties and things like that. And then you have aspects which actually implement the actual work that the engine has to do. So you have one for rendering, you have one for input handling, and another one for animations and so on. And every aspect will have its own representation mapping the front-end nodes. So there's a roughly one-to-one mapping between front-end and back-end nodes. Of course, the input aspect doesn't care about things specifically related to rendering, and so it would only map some of the things that are that come from the front-end nodes, but not necessarily everything. So one of the things that these aspects do is that they need to run some processes, and in order to do that, all these processes are encapsulated in jobs. So each aspect will have a number of jobs that need to be run at every frame in order to do whatever needs they need to do. So for example, the render aspect might need to calculate bounding volumes, then it might need to calculate draw calls and so on, and then the input aspect might do other work. The animation aspect will progress animations and so on. So every aspect has a number of jobs that it needs to do, and that needs to be done at every frames. All these jobs are executed in a thread pool using Qt's thread pool mechanism. So an overview of how this was put together before 5.14 is that all your main objects, your API object that you create instances in your applications, they live in the main thread. Obviously, the state of these objects needs to be synchronized with the backend nodes. So we have something called the change arbiter, which looks at the changes of state of these main thread objects. It basically listens to change signals on all the properties. And when one property changes, it creates a little instance of a message that gets put on a queue, and the message records which object and which property has changed and what the new value is using a queue variant. All these messages get put on a queue, and then at every frame inside the simulation loop, that queue basically gets processed and all the messages get dispatched to the various aspects. Okay, once all these messages have been dispatched, we know that the backends are synchronized with the front end. The state has been copied across, and we can then run the jobs. So the aspects provide a list of jobs that need to be run, and these jobs have dependencies. You need to calculate the bounding volume before you can do picking and so on. All of these jobs are then executed on the thread pool, and one of these jobs is actually responsible for submitting actual draw calls. So one of the jobs for the rendering aspect will actually submit the render command, and then it will say, okay, I've submitted those, it's okay to proceed to the next frame, and then you go around another loop again. Okay, so basically here what we're having is we have lots of threads, where there's 3 principal threads: the main thread, the aspect thread, and the rendering thread, plus all the threads on the thread pool. And then we have lots of messages that go between the threads in order to propagate the changes of properties. Okay, and the messages don't go only from main thread to aspect thread; they also go to the other way around. So, for example, the animation aspect will change the translation of an object, and that value needs to be propagated back to the main thread so that the application can track the change in that value. So this was designed this way because it's essentially lock-free, apart from the synchronization around the thread pool and the synchronization on we're using thread-based primitives to handle the message queues. So essentially very little locking. However, there is a fair amount of synchronization between the threads, and there's also a lot of memory allocation. So every time the change is recorded, we need to create one of those change messages, which allocates memory, and that has inside a string, and it has a Q variant, which takes time, and so on. So all of that quite costly. There used to be a pool of reusable messages instances, but that was removed by the company in some refactoring code pass. So unfortunately, we're left with lots of allocations. So what we did in Final 14 is actually overall rewrite this thing. The first thing we did is remove the aspect thread, so that the aspects live also in the main thread. That means we have a lot less synchronization problems between the main thread and the aspect thread, and in particular, because they live in the main thread, it's safe for backend nodes to access their front-end counterpart. So the whole thing without the thread becomes much easier to maintain. It makes the integration with the QtQuick renderer a lot simpler. And it allows optimization, specifically when you can directly sync the front end and the back end nodes. So how it looks like now is everything lives on the main thread. And once at every frame, we can basically, there's a synchronization steps where each aspect tells, we still have a change arbiter, but that only tracks which nodes have changed. So a little bit like the QtQuick scene graph changes work. We keep track of which node changes, and then here, when we sync the front end changes, we can tell the backend node, you have changed, this is a pointer to your front end object, copy the data that need to copy, and so on. So you no longer have to allocate messages, you can do direct syncing of the data. We still have the message syncing step here, which is still there just for compatibility in case some of the users have created their own aspects, but it's no longer used by the Qt core, the aspects that ship with Qt. And then we still have the jobs which run on the thread pool. And then we have another syncing step where the jobs can actually copy the data. So the jobs, because they're running on the thread pool, it's not safe for them to access the main thread objects directly. So once they're all done, each job gets an opportunity to, in the main thread, copy the results of its calculations back to the main thread API objects. So now the jobs that run as part of the animation aspects can directly access the properties on the foreground, the main objects. And in terms of performance gains, this has been proven to be really really interesting. So there's this example I'm not going to run, just a screenshot of it here. Basically, we load an object and then we create 1,000 instances of it, and on every frame we rotate each object around the 3 axes. Okay, so every object gets rotated around X and Y and Z axis on every frame. So that's 3 properties, 3 messages, time 1,000 objects, times 60 frames per second. So a 2-second run of this demo would actually allocate 1.2 million instances of message classes. So obviously it's a huge amount of allocation. On desktops you tend to not notice it too much, but on some systems, especially embedded systems, and on systems where the memory allocation is not optimized, where it might actually lock all the threads when one thread is allocating memory, that basically kills the performance pretty drastically. So now that number of allocations in 5.14 went from 1.2 million for this example down to 0. So we're no longer allocating any messages at all for the for this example here. Okay, 5.15 we went one step further. We actually removed the rendering thread also. So if we go back here, we still had the rendering thread and the draw calls were issued in the rendering thread. 5.15 removes that, and the draw calls are executed either in the main thread or in whatever thread QtQuick is using when you're using the Scene3D and the QtQuick embedded version of Qt3D. So depending on how the scene graph thread is set up, it might be the main thread or it might be another thread. It's platform dependent, and yeah, it can be controlled by the user. Other things we added in 5.15 is performance tracking. We have so it's been always a bit difficult to find out where performance, where the time was spent in Qt3D applications, mostly because people use that and they don't know 3D really well, so it's hard to tell where the time is spent. So there's a little overlay that was introduced in 5.15, which will print things like what the current FPS is, how many jobs the various aspects are actually executing on every frame, how many render views you have. A render view is a pass in the rendering, how many draw calls you have, so the number of commands that actually get executed, the total number of vertices and the total number of primitives. So for example, in this car here, you have 390,000 triangles. And they come from 89 different geometries. Okay, and you have 17 textures, but only 9 of them are actually used in this particular frame. So that gives you an idea of how much data is in play in your application, and you can have lots of other information about it. It will actually also let you dump the scene graph and the frame graph and the render views that are created by Qt3D. So here, for example, you can see it as an overlay. You can have a dump as a textual representation where you have the details of the render view. So a render view is a pass in the rendering. In this case, this example, the previous one with a car, there were 8 render views. There were 8 different passes to make up the final frame. In this one, you've only got 1, and that render view, you can see here, it draws a sphere and a donut. And you can see you have the render view, some details about it, and you can see it has 2 draw calls, one for 4,000 triangles and one for 480 triangle. I think the 4000 must be the donut, and the 480 is the sphere. So you can see your 2 draw calls there. And that basically, drilling down like that gives you a lot of details about what it is that you're drawing. And then you can use some other external tools if you need to actually track the time OpenGL spends. But this is a good way of drilling into the data here. One thing you can also do is enable job profiling. So as I mentioned, at every frame, QtDay runs a lot of jobs, and if you tick this little tick box here, you can enable job profiling, which will basically dump all the time spent on all the jobs at every frame into a file. You can also enable that by exporting an environment variable called QtDay trace enabled. And as I said, at every when that is true, at every run, it will create a file with the time spent on every job. So which jobs are run and how long they're run, and then you can use another tool that's available on GitHub that we don't ship with QtDay because it's a bit rough around the edges. But that basically you examine those job files and find out where time is spent. And you can see, for example, in this frame, there's 2 jobs here. Well, there's a job here that takes 7 milliseconds at every frame. So this is obviously one of the long ones. So you might, if you're slow, try and find which jobs is slow, and that will give you, combined with the data inspector, will give you an idea of what it is that is causing your application to be slow. So that's roughly everything that changed in 5.14 and 5.15. So yeah, 5.15 has been out for nearly 6 months now, I guess. So it's old history. And the rest of the talk, I'd like to talk about the things that we've been doing on Qt 6. There's 2 main things we've been doing. One is change some of the API, but what I'd like to talk about first is some of the things we're doing on the actual rendering backend. We did work in 5.14 and 5.15 to basically isolate the rendering backend of QtDay's render aspect into a plugin. So all the code that actually depends on OpenGL has been moved into a plugin with an abstract API. The idea is that you could then write other plugins to use something else apart from OpenGL to do the actual rendering. At the same time, although we didn't know about it at the time, but at the same time, the Qt company worked on something called RHI, which is a rendering hardware interface, which is basically a private API in QtBase, which is a layer around Vulkan, Metal, DirectX, and OpenGL, and it has principles that are very similar to what you have in model APIs such as Vulkan and Metal. Basically, if you use that API, it will issue the draw calls in whatever is the best actual API for your platform. So if you're using RHI on the Mac, it will issue do draw calls in Metal. On Windows, I think we'll use DirectX by default. On Linux, we'll have Vulkan if it's available. Other platforms will just use OpenGL, or at least OpenGL ES. Now the Qt company did this for the QtQuick rendering, so its API is targeted towards QtQuick rendering. All the principles there, which is why for OpenGL, for example, it targets basically ES, which is what QtQuick uses mostly. So 2D API. but it's quite a capable API, and it abstracts you from using that. As I said, it's private API. You shouldn't really use it in your own applications. But in Qt3D, we've been able to create a separate render plugin which uses RHI, which in turn will pick whatever the actual graphics API is available on the platform. Okay, that means that now, if you compile your application against Qt6, the RHI backend will be the default, and on Windows, it will use DirectX to do the rendering. On the Mac, it will use Metal, and so on, with quite drastic performance improvements in a lot of cases. Okay, so RHI is the default backend. The OpenGL backend is still there. So unlike QtQuick, we haven't removed it. It's still there. It's still maintained. There's an environment variable you can set for Qt3D to actually select which API to use. So it's called Qt3D renderer, and you can set it to RHI, which is the default, and you can set it to OpenGL. If you select RHI, you can actually force RHI to use a specific API. So for example, on the Mac, it would default to Metal, but you can actually force it to use OpenGL if you wanted to by setting the QSG RHI backend environment variable. Okay. So that RHI has some limitations in terms of features. As I said earlier on, it was targeted to QtQuick rendering, so it's basically designed to support that. So not all texture formats are available. The things like memory barriers are they're tricky to handle. Doesn't have geometry shader support or things like that. It also has some sort of design restrictions, in particular when it comes to things like multi-threading. So on the modern APIs like Vulkan and Metal, they're designed to be heavily multi-threaded. But because RHI itself, its an internal design, makes it impossible to use it in multiple threads. You can't really take benefit of all the multi-threaded support of the underlying graphic API. The GL backends has some limitations also. It's targeting it essentially to ES2, and it has some other design decisions, like for example, you can't do a partial clear of the screen. It can only clear the entire screen and only at the beginning of the frame. Which has some impact as to some of the things you can do in Qt3D's frame graph API to control the order in which things are rendered and doing more advanced effects. So you have to work around some of the limitations of RHI. If it's really problematic, you can force Qt3D to use the OpenGL backend. And then you can have access to geometry shaders, for example, and so on. But it's still a useful addition to Qt3D using the RHI backend. Hopefully, we'll be able to work. RHI will evolve to remove some of those limitations, and we will also look at using Qt3D's plugin API to do other rendering backends that might target Vulkan directly or Metal directly, and so on. But for Qt6.0, this is the first target, is to support RHI, and it's quite beneficial in terms of performance and frame rate and so on. Other changes we've made in Qt6 in the API. So the backend renderer was going to be mostly transparent for the majority of users. You'll just get better performance. but there's lots of other changes that were made in Qt 6 for the API. Sorry. In particular, we've been working on some of the way, changing slightly the way that geometry is represented. So a geometry for a mesh is going to be a buffer and an array of data, but obviously you have to tell the rendering backend how that data is structured. So in order to do that, you need to create Q attributes. So for a vertex in a mesh, for example, will have a coordinate, it might have texture coordinates, might have normals, might have cutter, and so on. So for each of those, you need to create an attribute and assign that to a geometry. So that describes how the data in the buffer or buffers is structured. That's not enough to give you all the details of a mesh. You also need to tell OpenGL what type of primitive it is and some other information. Now all of this information already existed in Qt3D, of course, and it was assigned to QGeometry renderer in the render aspect. Unfortunately, it came apparent that it might be useful for geometry to be provided to not just the render aspect, but also other aspects. For example, if you have physics simulation aspect, or if you have a collision detection aspect, they both would need to manipulate geometry. But normally they couldn't access the QGeometry renderer because that's a renderer aspect class. So we're introducing QGeometry view, which is exactly the same thing as QGeometry renderer in terms of specifying what a mesh is. But one, it's in the core aspect, and two, it's not a component that you attach directly to an entity. It's basically an object that you can assign as a property of another component. So QGeometry view is a new class, and it uses the existing geometry attributes and buffer classes to completely define a mesh. Unfortunately, this leads to some source breaking changes in Qt 6. So you might have to change your source code to compile your applications against Qt 6. So the Q buffer, Q attributes, Q geometry classes, they have moved from the Qt3D render module to the Qt3D core module. Okay. In QML, this is mostly transparent. Unless you've been using module aliases, you shouldn't have to change anything. In C++, though, it means that the namespace in which these classes have been defined and the path to the includes has changed. So a little trick for you, if you need to compile your source code against both Qt 5 and Qt 6, you can test the version. You would have to, of course, use different include paths for these particular classes because they've changed modules. And then your little trick is to use a namespace alias from C++. So here we're declaring a Qt3D geometry alias for the Qt3D core namespace. And if it's on Qt 5, then that same alias will be for Qt3D render. And then all the rest of your code, you need to change it once to say Qt3D geometry rather than Qt3D render, which it probably was before. And from there on, your application would compile both against Qt 5 and Qt 6. Just a little C++ trick here. Slightly unfortunate change, but couldn't be avoided at this point. QGeometry renderer, which was the previous way of defining geometry, that still exists there, but it has a new property, which is a pointer to a QGeometry view instance. Okay, all the old API is still supported, so you don't need to rewrite all your code that creates geometry renderers just yet, but we are going to deprecate it in Qt 6 timeline, and it will be removed in Qt 7. Okay, other change in Qt3D is the way it handles bounding volumes. Now, Qt3D has always had to calculate bounding volumes. So the bounding volume is calculating based on a geometry, calculating the place that it occupies in space. So Qt3D calculates a bounding sphere around all the object, and the reason it does that is to do things like view frustum coding, to basically quickly decide that an object is outside of the viewport, so it doesn't need to be rendered. It also accelerates picking and lots of other things. And Qt3D maintains also a hierarchy of these. So for the scene graph hierarchy, it will calculate the bounding volume for every entity. It will calculate the bounding volume that encapsulates the entire subgraph. Some limitations, though, needs to be updated. That's obvious. One of the limitations is that these data were internal to the rendering backend, but it's quite common for the user to actually need those values for its own work. So it would have to recalculate in those values themselves, which it's not difficult, but it's a bit of a pain. Another thing that is the user might actually know the values because it calculated the mesh in the first place, or it's using a file format where the bounding volume is recorded. So why not provide them to Qt3D and avoid the cost of having to calculate them? So in order to support all of that, we're introducing a new component called QBoundingVolume. And that basically has the possibility to read and write the bounding volume, the size of the bounding volume around a geometry. So you of course need a geometry view in order to specify what the mesh is. And then you get two read-only properties called implicit min point and implicit max point, which are the minimum and maximum points of the axis aligned bounding volume around the geometry. Okay, now there's also a Boolean geometry that says Boolean property, that says are those implicit points valid? And the reason for that is that the calculation of the bounding volume is done in a job, and so that's done at every frame. So setting the geometry and reading those implicit and maximum point is actually an asynchronous operation. So if you set the geometry, you have to wait one frame before those 2 points, the data on those 2 points becomes valid. So that's what the Boolean flag is there for. If you can't wait for frame, you can call QBoundingVolume update implicit bounds, which will calculate those values there and there. Of course, it will block the main frame while it's doing the main thread, while it's doing that. Okay. Now this QBoundingVolume is the base class for QGeometryRenderer, which means that if you have a geometry renderer or a mesh which derives from QGeometryRenderer, you can actually query the minimum and the maximum points to get the size of the bounding box around the point, the load-in mesh. So you can load a mesh and get the updated values here in QML. So this would happen on the frame after that the mesh was actually loaded. Okay, to read the values. So that's an easy way of accessing the bounding volume of a geometry, but you can use the same class to actually set the bounding volume if you know it. So there's two other properties which are read-write properties, and if you set them both, the min point and the max point, this will basically stop Qt3D's backend from calculating the bounding volume. It will just use those min point and max point, and it will not have to iterate through all the vertices in order to calculate the bounding volume. So you can, if you know what it is, because your file format stores that, or because you've calculated the mesh from some algorithm and you know what the bounding volume is, then you can actually set it like that explicitly, and that will stop Qt3D from calculating. Another thing you can do, if you don't know what the values are, but you know that you have another object that completely wraps your geometry, but is much simpler, for example, it could be just a cube, then you can actually use the bounding volume component directly. So here I'm loading a mesh from a file, and I know that this mesh is going to fit inside a cube of a certain side. So I can create a bounding volume and give it a mesh that is going to be of the appropriate size. Okay, so here I'm just using a cube, and I could give it the size of a cube because I know that the mesh here is the right size. So when it comes to calculating the bounding volume of this entity, it won't calculate, Qt won't calculate the bounding volume of the loaded mesh. It will use this much simpler bounding volume here. Using this simplified mesh is actually something you can also use for picking. So there's two picking modes in Qt. There's a fast picking mode, which basically just looks at the bounding volume. And if your picking ray intersects the bounding volume, it considers that the object has been picked. Sometimes that's not what you want. You need more details. You need to find out where on the surface it is, or if the shape of it is not ideally represented by a sphere, which is the default internal bounding volume of that Qt maintains. Then you might have to switch on detail picking, so primitive picking, and in that case, it needs to look at every primitive. So if you have 10 million vertices, it will need to use 10 million vertices. If you have 20,000 triangles, it will need to look at the 20,000 triangles, and so on. Which can become very slow and costly. So one thing you can do in Qt 6 is to use a simpler geometry in order to support this detail picking. So you can create your two components, the geometry renderer, which is actually going to be rendered, and then you can use the picking proxy, which is, they're both going to have views, and the actual view is going to be a detailed one, and the picking view is going to be a much simpler mesh, where picking is going to be much quicker to calculate. So for example, here you have a mesh of a bunny here. You could use the left one to render and the right one to do picking. The right one has only 5% of the triangles that the left one has. So it's going to be a lot quicker to decide whether the ray intersects with that shape or not. Obviously, if you're doing a mesh editor that needs to move an actual mesh of the vertex, then you can't use this technique, but it's because the point picked on the right bunny might not exist on the left one, so it's just an approximation of it. But lots of cases where it might be useful to use this kind of technique. I'm going to be short on time, so I'm going to skip some other techniques. But we basically made public some API that was private on the aspect and in the aspect jobs, which makes it easier to do the synchronization things that I was talking back at the beginning of the talk. And what I'd look to talk about for the rest of the time I have is Kuesa. So Kuesa, I talked about it at this conference last year, is a library that sits on top of Qt, so it's going to benefit from all the work we've been doing on 5.14, 15, and now Qt 6. In terms of performance, things like that. What it is basically it's a workflow for integrating assets between the creation tools. So think Blender, 3D Studio Max, Maya, the kind of tools that your designers will work with, and integrate the results of all that in your applications. In order to support that, it uses GLTF as a file format, and GLTF can contain lots of information. So it has the geometry, it has lots of materials, it also has animations and so on. And it basically lets developers import all of that into the applications with no transcribing, there's no intermediate file format and so on. You have direct access to the GLTF tool, which means the integration is completely lossless. And in particular, the update, if the designer changes the model, the update is very easy. And from within your application, you can access and modify the geometry, the materials, the animations, and so on. So it lets you, import the objects like that and have really nice rendering. This uses physics-based rendering that is specified by GLTF2, and you get some really nice rendering here. And it's very easy to integrate in your application. So I have a little example here, which if I run it quickly, it's your obligatory car-based demo that all these toolkits have. And so I have the model and all its materials and all of that specified in Blender, exported to GLTF2, and that also includes animations. So the position of the camera is actually controlled. It was actually designed in Blender, and that gets all exported, all the animations from the doors and the hood, all specified in Blender, and then it loops here. But then in the application, you have complete control over those. You can go and play the animations, change the speed, change the direction, and so on. And Kuesa also comes with tools, so the integration is very easy. You have View 3D, and you specify the source and the name of the camera here. You can, if you have animations, you need to load up animations, and the link between so all of these animations are basically, the name of those are defined, like the camera, are defined in Blender by the designer. So you just need to sit down with him and ask him for the name of the animations, and they will just fill those in. And then you can just use this animation player to manipulate those animations and start them. You can also have other things with Kuesa, like one of the things you quite often want to do is to track the screen projection of a 3D object. So where is a 3D object projecting on the screen? So in this case, we have an object which we actually don't see, but is positioned just above the engine here. And we can use the screen space projection of that object in order to position some QtQuick items. So in this case, this overheating text is just a QtQuick item which is animated, but the position is automatically updated by Kuesa by tracking the projection of a 3D point on the screen here. So you can see the text moving about as I rotate, and as the position of the tracker is also animated here. Using the same trackers, you can actually manipulate the geometry. In this case, the pulsating of this red engine, the fact that it's moving here, this is controlled by QtQuick animations rather than the animations that are in the file. So you can mix and match the two things. Other things you can do with Kuesa, so I mentioned the easy integration, the animation, the screen space projection. You can also easily take a QtQuick scene and map it onto an object inside your 3D. So if you use a quick scene material here, you give it a name of the material. So the material is a texture in an object. So your designer would put an object in the 3D and give it a material and give it a specific name, and you would need to take your QtQuick item and map it onto that object. And then the item here is specified very easily, so that lets you embed one of those QtQuick demos that shipped. I forget what the name of that. I think there's a multimedia demo or something like that. And that's a QtQuick scenes which is mapped onto an object inside the scene at runtime and rendered on your 3D object. And it goes further than rendering, because you can actually interact with it and click on it. So if this was the same game demo, you could go and play the game in here inside your 3D scene and actually interact with those objects. So lots of useful things in Kuesa. It has some extensions to GLTF to do some more lightweight materials. So GLTF specifies PBR materials, which are really nice and shiny, but they are quite expensive to render, especially on embedded hardware. So Kuesa ships with a number of custom lightweight materials that you can use to do your rendering. It also comes with a tool to do model conditioning, so you can load the GLTF file, find out what the names of the various components are, find out how the complexity of them, how many meshes it has, how many vertices each mesh has, and so on. So you can tell your designer to maybe cool it on the number of triangles because it's going to be too slow to render. That's on. It also supports compressing the mesh using the Draco extension to GLTF2 and so on. So there's lots of things that this tool can help you do with. There's a command line version also to help you integrate those processing in your build system. And coming up in Kuesa is a number of things like fast asset loading, and support for multiple views, particles, reflections, shadow, casting shadows, and so on. We're also now supporting Maya as an authoring tool, which will be really useful for lots of clients, and a number of other things. So hopefully, went over time, but hopefully this is a lot of useful information for you for finding out what's new in Qt3D and in Kuesa. So now, if you have any questions, I'll take some of the time left to answer them. Thanks you very much for listening.
There we go. All right. Welcome back, everyone. And let's go ahead and get right into the Q&A with Mike.
Hi, everyone.
Hi there, Mike. Yeah.
Thanks for hanging around.
Absolutely. And thanks for your contribution. We're happy to have you here at QtDay, even if it is virtually this year.
Yes.
All right, let's go ahead and proceed with a question we have from Mateo, who says, is there any way to access animation names from Kuesa if the designer is not available, or is it an old job with no backup?
So you can do that in two ways, either using the sort of tool that we ship with Kuesa, the asset editor, which basically lets you pick on an object and find out what the name of that asset is. So that's the interactive way. Otherwise, you can access programmatically the names of all the assets that are defined, and just dump them and make a guess as to which one is the right name. So yeah, you can do that.
All right, awesome. Well, thank you for that. Let's see here. Okay, seems like that is our only question. I'll give people just a minute more to type anything. And in the meantime, I wanted to ask Mike if you had anything to say about your participation in QtDay.
Well, I suppose like most people who attended QtDay days last year, what I miss the most is the food. Yeah, so real food in Florence was quite good. No, I really miss, of course, the being on site and being with everybody. So yeah, hopefully next year.
Yeah, crossing our fingers. Luckily, we are able to do it remotely this year, though.
Yes, really good. We appreciate the effort you all put into this.
Of course. For passionate people like you, no problem. All right. Well, it looks like we don't have any other questions. So I guess that's it, unless you had anything else you wanted to add?
No, that's it for me.
All right, awesome. Well, thank you, Mike, and thanks for all of the participants also for sticking around. And Mike, we hope to see you, of course, live next edition of QtDay.
Yeah,
Thanks.
sure.
All right, have a great rest of your day. Thanks. Bye-bye.
Thank you. Bye.
All right, you all. So thank you for attending again. And like I said, if you liked this talk, you can definitely rate it on the agenda page of QtDay on the Bizzabo one. We appreciate your feedback. So we'll see everyone for the next talk, which is at 4:50 p.m. So in about 15 minutes from now. Thank you. Okay. And that one is Cross-Compiling Qt Applications with CMake by Burkhard Stubert. So hope to see you then. Thanks. Bye-bye.